Welcome to a lesson with Dr. Powell. Let's take a look at another example of decomposing a vector into a part along a plane and another part that's parallel to a line. So we're going to, this time, we're actually going to just say, well, let's take a plane and see what we can do with it, all right? The plane usually comes from the right inverse of a function. What if we started with the right inverse, which describes the plane? See these column vectors? We can map them out and plot them. Think 1 in the x direction, or -1 in the x direction for this guy right here, -1 in the x direction, and 1 in the y direction would be that vector. And then over here you have 2 in the x direction, 1 in the y, and -1 down. So you have two vectors describing this plane. Line them up like this. This could be like g, like a right inverse going back. Well, what function did it come from? Now, depending on what function it comes from, though, will determine what our line is that we're going to be working with, because the kernel of whatever that function is. So we can go ahead and actually what we can do is to find that function, we just simply compute a left inverse for this. Because if a matrix has a right inverse, then that matrix itself is a left inverse to the function we found as the right inverse. Okay, so how do we do that? Well, we need to do row operations on the left, okay, of this. And here's a sequence of row operations of different things that can be done. And in the process, the identity matrix, we can do this too. So the identity matrix would be done in the in this case would be, so this is the domain of G is R2 and the codomain is R3. So which is going to be the domain of F, but we work in that domain. So isomorphism, identity matrix, R3 to R3, and we apply these operations on it, and the end result is that row operations matrix. So doing so, we get this as we apply all the same row operations we need to get the Smith normal form to the identity matrix, and we get the row operations matrix. Now, if we just take the top two rows, that actually gives us a left inverse to this matrix right here. And so that could be your F. Okay. Now, if that's our F, here's just a little description. Let's actually, this would probably be a little bit unnecessary perhaps, but we actually can see right now what the kernel of this matrix is by thinking of the column operations, and then that we need to get the Smith normal form, and then we match up the zeros to here. Right now, this right here is so the corresponding column to the column of zeros is a basis for the kernel. Now this process even works because this was surjective, so that means that column operations will get us to Smith normal form. In fact, notice that this is a different right inverse than the one we started with originally, the describer plane. This would actually describe a different plane. But no matter what other plane we describe, the kernel actually, as long as we fix F as this, will always be the same. So we can just pull, this is just a little side note just for information's sake, but we didn't really necessarily have to do this, but we can see what the kernel is. Of course, we have a different right inverse, but we didn't really need that because it describes a completely different plane, so we'll throw it out. Okay, but at least it kind of gives us an idea of the kernel, but we didn't even have to do that necessarily, but we just did that because for illustrative sake, and we'll see why in a minute. Okay, so let's just take something in our domain, R3, domain of F, and we'll decompose it with respect to the kernel and the plane that was given by our original G right here. Now, in the process, let's see what happens. In fact, we'll actually see that we didn't really have to know what this kernel was as we go. So basically, all we're doing, though, is we're just putting 1, 2, 3 into F and then into G to come back into the domain, and we end up getting negative 11, 2, 3. So basically, put it into F, you put that into G, you get this, right? So these two guys should be in the same fiber, meaning their difference is actually in the kernel. So in fact, if you subtract the two, you'll notice that you actually get this guy, which was in the kernel that we just saw, right? Okay, so in fact, this right here plus negative 11, 2, 3, which is in the plane, so we have a plane vector plus a kernel vector is equal to 1, 2, 3. We have just successfully decomposed this vector in terms of a plane vector and one that's in K, following the idea of, again, of this decomposition idea that we have GR direct sum with the kernel. So meaning that a basis for this and a basis for this together are linearly independent, and we can uniquely decompose things according to those bases vectors. In particular, you have a unique thing in here and a unique thing in here added together. So this is a unique process. Thanks for watching.